In the previous chapter, we talked about how to avoid memory fragmentation by breaking process memory requirements down into smaller pages and storing the pages non-contiguously in memory. However, the entire process still had to be stored in memory somewhere. In practice, most real processes don't need all their pages, or at least not all at once, for several reasons. Error handling code is not needed unless the specific error occurs, some of which are quite rare. Arrays are often oversized for worst-case scenarios, and only a small fraction of the arrays are actually used in practice. Certain features of certain programs are rarely used. The ability to load only the portions of process that were actually needed, and only when they are needed, has several benefits. The programs could be written for a much larger address space, like a virtual memory space, than physical exists on the computer. Because each process is only using a fraction of their total address space, there is more memory left for other programs, improving CPU utilization and the system throughput. And less I/O is needed for swapping process in and out of RAM, speeding things up. This figure shows the general layout of virtual memory, which can be much larger than physical memory. The virtual address space of a process refers to the logical or virtual view of how a process is stored in memory. Typically, this view is that a process begins at certain logical address, say address 0, and exists in contiguous memory. Recall from the previous chapter 9, so that in fact the physical memory is organized in page frames, and that the physical page frames assigned to a process may not be contiguous. It is up to the Memory Management Unit, MMU, to map logical pages to physical page frames in memory. Note that the address space shown in this figure is sparse. A great hole in the middle of the address space is never used unless the stack or the heap grow to fill the hole. Virtual memory also allows the sharing of files in the memory by multiple processes with several benefits. The system libraries can be shared by mapping them into the virtual address space of more than one process. Processes can also share virtual memory by mapping the same block of memory to more than one process. Process pages can be shared using a fork system call, eliminating the need to copy all of the pages of the original process. Demand paging in virtual memory is to load the pages only when they are demanded during program execution. Pages are never accessed, are thus never loaded into physical memory. So the basic idea behind demand paging is that when a process is swapped in, its pages are not swapped in all at once. Rather, they are swapped in only when the process needs them and demand. This is termed a lazy swapper, although a pager is more accurate term. The basic idea behind paging is that when process is swapped in, the pager only loads into memory those pages that it expects to process to need right away. So pages are not loaded into memory are marked as invalid in the page table using the invalid bit. The rest of the page table entry may either be blank or certain information about where to find the swapped out page on the hard drive. If the process only ever accesses pages that are loaded in memory, so it's called memory resident pages, then the process runs exactly as if all the pages were loaded into the memory. On the other hand, if a page is needed that was not originally loaded up, then a page fault trap is generated, which must be handled in series of steps. Step 1. The memory address requested is first checked to make sure it was a valid memory request. Second, if the reference was invalid, the process is terminated. Otherwise, the page must be paged in. Third, a free frame is located, possibly from a free frame list. Fourth, a disk operation is scheduled to bring in the necessary page from disk. This will usually block the process on an I/O wait, allowing some other process to use the CPU in the meantime. Fifth, when the I/O operation is complete, the process page table is updated with the new frame number, and the invalid bit is changed to indicate that this is now a valid page reference. 6. The instruction that caused the page fault must now be restarted from the beginning as soon as this process gets another turn on the CPU. In an extreme case, no pages are swapped in for a process until they are requested by page faults. This is known as a pure demand paging. In theory, each instruction could generate multiple page faults. In practice, this is very rare due to locality of reference. We will see in a later section. This will result in reasonable performance from demand paging. The hardware necessary to support virtual memory is the same as for paging and swapping. A page table and a secondary memory. Swap device with a swap space is introduced in later chapters in this book. A crucial part of the process is that the instruction must be restarted from scratch once the desired page has been made available in memory. For most simple instructions, this is not a major difficulty. However, there are some architectures that allow a single instruction to modify a fairly large block of data, which may span a page boundary. And if some of the data gets modified before the page fault occurs, this could cause problems. One solution is to access both ends of the block before executing the instruction, guaranteeing that the necessary page get paged in before the instruction begins. When a page fault occurs, the operating system must bring the desired page from secondary storage into main memory. To resolve page faults, most operating systems maintain a free frame list, a pool of free frame for satisfying such request. So free frame must also be allocated when the stack or heap segments from a process expand. Operating systems typically allocate free frames using a technique known as a zero fill-on demand. Visual Field on Demand frames are zeroed out before being allocated, thus erasing their previous contents. When a system starts up, all available memory is placed on the free frame list. Obviously, there is some slowdown in the performance hit whenever a page fault occurs, and the system has to go get it from memory. But just how big a hit is it exactly? There are many steps occur when servicing a page fault, listed as followings. Also include those steps. Some of those steps are optional or variable. For the sake of the discussion, suppose that a normal memory access requires 200 nanoseconds, and servicing a page fault takes 8 milliseconds. So 8 milliseconds equal to 8,000 K nanoseconds. Or we can say it's a 40 K times a normal memory access. With a page fault rate of P is on a scale from 0 to 1. The effectiveness access time, EAT, is 1 minus P multiply 200. So 1 minus P is the percentage that doesn't need page fault. It just have a memory access. So P multiply 8,000 K, that's for the page fault. Result is 200 plus 7,999,800 multiply P. So it depends heavily on P. Even if only one access in 1,000 causes a page fault, P is 1 over 1,000. It's 0.1%. The effective access time drops from 200 nanoseconds to 8.2 microseconds, a slowdown of a factor of 40 times. In order to keep the slowdown less than 10%, the page fault rate must be less than 0.000025 or 1 in 399,990 access. So basically, the page fault should be less than 1 page fault in every 400K memory access. The page faults can be very detrimental to effective memory access time, though it is extremely important to prevent the page fault rate from becoming excessive. An operating system may be designed to limit paging between main memory and the file system because throughput to swap space is faster. Windows XP, Linux, and the Solaris use copy on write with fork. Instead of copying the entire parent process, the system copies only the pages on which the parent or child actually writes. The idea behind a copy on write fork is that the pages for a parent process don't have to be actually copied for the child until one or the other of the process changes the page. They can be simply shared between the two processes in the meantime with a bit set that the page needs to be copied if it ever gets written to. This is a reasonable approach since the child process usually issues an execute (exec) system call immediately after the fork. Obviously, only pages that can be modified even need to be labeled as copy on write. Code segments can simply be shared. Pages used to satisfy copy on write duplications are typically allocated using zero fill on demand, meaning that their previous contents are zeroed out before the copy proceeds. Some system provides an alternative to the fork system call called virtual memory fork, VFork. In this case, the parent is suspended, and the child uses the parent's memory pages. This is very fast for process creation, but requires the child not modify any of the shared memory pages before performing the execute system call. In essence, this addresses the question of which process executes first after a call to fork, the parent or the child. With VFork, the parent is suspended, allowing the child to execute first until its calls execute, sharing pages with the parent in the meantime. Physical memory may become over-allocated. There may be no free frames when a page fault occurs. The standard solution is called page replacement. In order to make the most use of virtual memory, we load several processes into memory at the same time. Since we only load the pages that are actually needed by each process at any given time, there is room to load many more processes than if we had to load in the entire process. However, memory is also needed for other purposes, such as I/O buffering. And what happens if some process suddenly decides it needs more pages and there aren't any free frames available? There are several possible solutions to consider. So physical memory may become over-allocated. There may be no free frames when a page fault occurs. The standard solution is called page replacement. Please click on the link to view the page replacement. I want to talk about the second chance algorithm again. The second chance algorithm is essentially a first in, first out, except the reference bit is used to give pages a second chance at staying in the page table. So when a page must be replaced, the page table is scanned in, first out in a circular queue manner. And if a page is found with its reference bit not set, then that page is selected as the next victim. However, if the next page in the FIFO does have its reference bit set, then it is given a second chance. So the reference bit is cleared and the FIFO search continues. If some other page is found that didn't have its reference bit set, then that page will be selected as the victim. And the page, the one being given the second chance, will be allowed to stay in the page table. If, however, there are no other pages that don't have their reference bit set, then this page will be selected as the victim when the FIFO search circles back around this page on the second pass. If all reference bits in the table are set, then second chance degraded to first in, first out, but also requires a complete search of the table for every page replacement. As long as there are some pages whose reference bits are not set, then any page reference frequently enough gets to stay in the page table indefinitely. This algorithm is also known as a clock algorithm, from the hands of the clock moving around the circular queue. The enhanced second chance algorithm looks at the reference bit and the modified bit, which is a dirty bit, as an ordered page, and it classifies pages into one of four classes. 00, so neither recently used nor modified. 01, not recently used but modified. 10, recently used but clean. And 11, recently used and modified. So this algorithm searches the page table in a circular fashion in as many as 4 passes. It looks for the first page it can find in the lowest numbered category. For example, it first makes a pass looking for 00, and then if cannot find one, it makes another pass looking for 01, etc. The main difference between enhanced second chance algorithm and the non-enhanced version is the preference for replacing clean pages if possible. There are a number of page buffering algorithms can be used with the previous mentioned page replacement algorithms to improve overall performance and sometimes make up for inherent weakness in the hardware or the underlying page replacement algorithms. We can maintain a certain minimum number of free frames at all times. When a page fault occurs, go ahead and allocate one of the free frames from the free list first, to get the requesting process up and running again as quickly as possible, and then select a victim page to write to disk and free a frame as a second step. We can keep a list of modified pages, and when the I/O system is otherwise idle, have it write these pages out to disk, and then clear the modified bits, thereby increasing the chance of finding a clean page for the next potential victim. Keep a pool of free frames, but remember what page was in it before it was made free. Since the data in the page is not actually cleared out when the page is freed, it can be made an active page again without having to load in any new data from disk. This is useful when algorithm mistakenly replaces a page that in fact is needed again soon. Some applications, such as database programs, understand their data accessing and caching needs better than general-purpose operating system, and should therefore be given the privilege to do their own memory management. Sometimes such programs are given a raw disk partition to work with, containing raw data blocks and no file system structure. It is then up to the application to use this disk partition as extended memory or for whatever other reasons it sees fit. We said earlier that there are two important tasks in virtual memory management: a page replacement strategy and a frame allocation strategy. This section covers the frame allocation strategy. Please click on the link to view the video. When it replaces a page, the operating system selects a frame used by process X and loads it with a page needed by process Y. Under a global page replacement policy, X and Y don't have to be the same process. Under a local page replacement policy, X and Y do have to be the same process. Global replacement policies are more common, perhaps because they allow the number of frames allocated to a process to change according to changing need. With global replacement, ideally there is a Robin Hood effect. The operating system steals frames from rich processes that don't need them and gives them to poor processes that do need them. If everything works out perfectly, then each process has the frames it needs to maintain a low page fault rate. This should result in high average throughput. On the other hand, there are other ways to dynamically alter the number of frames allocated to each process. If we use such an allocation strategy in conjunction with the local page replacement policy, might we allow process finer control over their own page fault rates? An operating system typically utilizes minimum and maximum thresholds to trigger one or more page replacement process, often called reapers. When the number of free frames drops below the minimum threshold, the reaper replenishes the supply of free frames by taking frames away from user process. The reaper sleeps when the supply is above the maximum threshold. Many multi-process systems have multiple system boards, each with multiple CPUs and some primary memory. This usually means the CPU can access the memory on its own system board more quickly than the memory on other boards. This is non-uniform memory access, NUMA. An individual thread tends to run slower on a NUMA system than on a system with uniform memory access. However, NUMA systems support greater number of CPUs, and thus they can have higher levels of parallelism and throughput. On NUMA system, it is desirable for the operating system to allocate all primary memory for a process on one particular system board, and to ensure that the process executes on a CPU on that same board. This result is likely to be high cache hit rates and short memory access times. If the process is multi-threaded, this manner of scheduling is more challenging. Linux and Solaris are examples of operating systems that have approached to solving this kind of problem. They have hierarchies of CPU and memory. Linux has scheduling domains and Solaris has L groups. These are groups of a CPU and memory areas that are mutually close, meaning that the latency between each pair of elements is low. For a multi-threaded process, the operating system tries to assure that all threads use CPUs and memory in just one of the groups, or in mutually nearby groups. If a process cannot maintain its minimum required number of frames, then it must be swapped out, freeing up frames for other processes. This is an intermediate level of CPU scheduling. But what about a process that can keep its minimum, but cannot keep all of the frames that it is currently using on a regular basis? In this case, it is forced to page out pages it will need again in the very near future, leading to large number of page faults. A process that is spending more time paging than executing is said to be thrashing. Suppose the degree of multiprogramming is very low. Say, to use an extreme example, there are only 2 or 3 active user processes. In that case, it will be likely that all those processes will be waiting for I/O at the same time quite often. At those times, the CPU will be idle and the CPU utilization is low in such a system. Assuming there is adequate memory available, will probably help utilization if we increase the degree of multiprogramming. On the other hand, if the degree of multiprogramming is very high, and if physical memory is over-allocated, then it is likely that there will be a lot of thrashing going on. In that case too, the CPU utilization may be quite low because often all processes will be blocked, waiting for paging and the other I/O operations to complete. In this case, it will only make things worse to increase the degree of multiprogramming. According to the principle of locality, the typical process usually spends relatively long periods of time accessing a relatively small locality. A locality is a subset of its text and data that the process has been accessing recently. Relative to memory access time, the locality of the processes tends to change very slowly. According to this view, the process will not thrash as long as it has enough frames to hold all or most of its current locality. The locality model notes that processes typically access memory references in a given locality, making lots of reference to the same general area of memory before moving periodically to a new locality, as shown in this figure. If we could just keep as many frames as are involved in the current locality, then page faulting would occur primarily on switches from one locality to another. For example, when one function exits and another one is called. Another example is a process remaining in one locality for a long time. Consider how a process acts while it executes a loop. The only instructions the process accesses are the instructions of the loop body and the instructions of the loop control. Quite possibly, the process will only access a small portion of its data while executing the loop. It is a very common thing for a process to spend a long time executing in a loop. The working set model is based on the concept of a locality and defines a working set window of length delta. Whatever pages are included in the most recent delta page references are said to be in the process working set window and comprise its current working set, as illustrated in this figure. The set of pages referenced during the last delta reference is called the working set. It is an approximation of the locality of the process. The goal of the operating system will be to use this approximation to help keep each process supplied with enough frames to hold its working set. If the operating system uses this approach, and if there are sufficient jobs available, it seems reasonable that the operating system will be able to keep the degree of multiprogramming high enough to attain good CPU utilization and low enough to prevent thrashing. When all processes have enough frames for the current size of their working sets, and when there is enough additional memory, the operating system will be able to place another job into memory. When memory is in short supply and the process cannot get enough for their working sets, the operating system might have to terminate process or swap them out and divide their allocations among the remaining processes that need more frames. The selection of delta is critical to the success of the working set model. If it is too small, then it doesn't encompass all of the pages of the current locality. And if it is too large, then it contains pages that are no longer being frequently accessed. The total demand, D, is the sum of the sizes of the working set for all processes. If D exceeds the total number of available frames, then at least one process is thrashing, because there are not enough frames available to satisfy its minimum working set. If D is significantly less than the current available frames, then additional process can be launched. The hard part of the working set model is keeping track of what pages are in the current working set, since every reference adds one to the set and removes one older page. An approximation can be made using reference bits and a timer that goes off after a set interval of memory references. For example, suppose that we set the timer to go off after every 5,000 references by any process, and we can store 2 additional historical reference bits in addition to the current reference bit. Every time the timer goes off, the current reference bit is copied to one of the 2 historical bits and then cleared. If any of the 3 bits is set, then that page was referenced within the last 15,000 references and is considered to be that process reference set. Final resolution can be achieved with more historical bits and a more frequent timer at the expense of greater overhead. Instead of the working set, to control thrashing, it is more direct and simple to work with the page fault frequency, PFF, of a process. Establish upper and lower bounds for page fault frequency. If the PFF of a process exceeds the upper bound, give the process more frames until the PFF goes below the upper bound. If the PFF of a process falls below the lower bound, then take frames away from the process until the PFF is above the lower bound. When there is a need to give frames to process and there are not enough frames, swap a process out and free its frames. When all processes have acceptable PFF and there is memory to spare, increase the level of multiprogramming. Note that there is a direct relationship between the page fault rate and the working set as a process moves from one locality to another. One possible drawback to PFF approach is that it is not sensitive to the difference between a change in size and a transition of the working set. If the working set is not changing its size, but merely transitioning from one locality to another, it may be better for performance not to give more frames to the process, but just to let process faults replace the pages that are being vacated in favor of pages new to the working set. Also, it will be good if the system keeps tracks of the working set of each process to help with pre-paging. When performing page replacement, it may be necessary to replace modified frames. The common way to handle such frames has been for the operating system to copy them out to the secondary storage before replacing them with their new contents. Unfortunately, the copy-out operation is time-consuming. Memory compression is an alternative to copying out. The operating system selects a set S of several frames for replacement, and then compresses all their contents to a size small enough to fit into a single frame. The operating system takes a frame X from the free list and puts the compressed data from S into X. Then the operating system puts all the items in S on the free list. The diagrams below indicate a before and after example. The operating system maintains a separate list for frames that contain the compressed contents of other frames. If a process faults on one of the frames that was compressed, the operating system services the page fault by decompressing the compressed frame, putting the compressed information in a free frame, and giving this frame to the process that faulted. It is difficult for mobile operating system to support swapping and paging. Most of them use memory compression. Tests have shown that the memory compression is faster than paging for desktop and laptop computers. Mac operating system has been utilizing memory compression since version 10.9. Mac OS still resorts to paging when the results from memory compression are not adequate. There is a trade-off between high compression and the speed of compression algorithm. The algorithm in current use are considered fast, and they reduce pages to about 30 to 50% of their original sizes. An operating system kernel typically has special memory allocation need. The OS may require kernel code and the data to be entirely resident in physical memory at all times, even though virtual memory is implemented for user process. The OS may need large numbers of data structures that have sizes that are not compatible with the page size. The size D of a structure may be smaller than the page, but the page size may not be a multiple of D. On the other hand, D may be larger than the page, but D may not be a multiple of the page size. If memory for such structure is allocated using standard frames, there can be unacceptable amount of internal fragmentation. Some hardware devices may be configured so they have to interact with a set of contiguous frames of physical memory. To facilitate conservation of memory, usually there are special memory allocation techniques and the methods available to the kernel. Buddy system. The model facilitates the allocation of memory in contiguous chunks of size equal to any power of 2, up to some limit. This diagram shows how a 32 KB chunk can be created for a request for 21 KB. By successfully dividing portions of a 256 KB segment in half, the number of bytes in an allocation is always the smallest power of 2, not less than the requested amount. Using the buddy system, it is easy to coalesce some adjacent deallocated chunks of equal size into single free chunks. The coalescence can cascade easily, leading to the reformation of larger and larger chunks, which then become available for reallocation. The problem with the buddy system is an internal fragment can be nearly equal to the requested amount of memory. Therefore, we cannot guarantee that the total internal fragmentation will be significantly less than 50% of the total memory allocated. The idea of the slab allocator is to use groups of pages as an array of one specific kind of data structure, say process descriptors, file objects, cephaloms, and so on. Each slab can be managed as with fixed-size partitioning. There is a single cache for each unique kernel data structure. Cache consists of one or more slabs. For example, the cache representing sophomores stores instance of a sophomore object. The cache representing process descriptors stores instance of a process descriptor objects, and so forth. The relationship among slabs, cache, and object is shown in this figure. When cache created, it filled with objects marked as free. When a new object for a kernel data structure is needed, the allocator can assign any free object from the cache to satisfy the request, the object marked as used. If slab is full of used objects, next object allocated from empty slab. If there's no empty slab, new slab will be allocated. This is very simple and there's no fragmentation in that the allocated objects are always the exact size required. The claim of no fragmentation should be taken with a grain of salt. The unallocated portions of the slabs may be considered waste, while they remain unused. Slab size is a multiple of the frame size. In Linux, a slab may be in one of three possible states. Full, all objects in the slab are marked as used. Empty, all objects in the slab are marked as free. Partial, the slab consists of both. The slab allocator first attempts to satisfy the request with a free object in a partial slab. If none exist, a free object is assigned from an empty slab. If no empty slab available, a new slab is allocated from contiguous physical pages and assigned to a cache. Slab started in Solaris, now widespread for both kernel mode and the user memory in various operating systems. Linux 2.2 had a slab, now has both slob and slub allocators. Slob, which stands for Simple List of Blocks, is for systems with limited memory. It maintains 3 list objects for small, medium, and large objects. From version 2.6.24, the slub allocator replaced slab as the default allocator for the Linux kernel. Slub reduced much of the overhead required by the slab allocator. For example, while slab stores certain metadata with each slab, slub stores these data in the page structure the Linux kernel uses for each page. Additionally, slub doesn't include the per CPU queues that the slab allocator maintains for objects in each cache. The major decisions that we make for a paging system are the selections of the replacement algorithm and an allocation policy, which we discussed early in this chapter. There are many other considerations as well, and we discuss several of them here. Pre-paging. Under pure demand paging, we expect a large number of page faults initially as a process begins execution. or as a process which has been swapped out starts being swapped back in. It may help overall performance if the operating system performs pre-paging. The idea of pre-paging is to load extra pages. When servicing a page fault, instead of only loading the page on which the process faulted, load additional pages on which the process is likely to fault soon. When swapping a process in, instead of demand paging, load the entire working set. Clustering is a simple technique that can help. Each page is a member of a cluster of, say, 4 to 8 pages. And whenever we page in a member of a cluster, we always page in any other members of the cluster that are not currently resident. Assume S pages are pre-paged, and a fraction alpha of this S page is actually used. So alpha is from 0 to 1. The question is whether the cost of the S multiply alpha saved page faults is greater or less than the cost of pre-paging. The cost of pre-paging is S multiply 1 minus alpha. So if alpha is close to 0, pre-paging loses. If alpha is close to 1, pre-paging wins. So when alpha is close to 1, the S multiply alpha is close to S. And the cost of pre-paging S multiply 1 minus alpha, because alpha is close to 1, so 1 minus close to 1, almost 0. 0 multiply S is almost 0. So the cost is almost 0. So the pre-paging wins. Normally, the architecture of the computer hardware determines the page size or some set of allowable page size. The trend in computer design has been to make page size larger and larger over the past 3 decades or so. Current page size range upwards to 4K bytes per page, even on mobile system. There's no agreement on what is the best page size. Arguments in support of big pages include when pages are bigger, the page tables can be smaller. When pages are bigger, it takes less time per byte to load pages into primary memory. When pages are bigger, we have fewer page faults. When pages are bigger, we have more TLB cache hits. Their arguments in support of a small page include the internal fragmentation caused when a process doesn't end on a page boundary will be less if page sizes are smaller. With smaller page size, we have a better resolution. Less unneeded material is paged into memory. Consequently, there is less total I/O and less waste the allocation of physical memory. TLB hardware is expensive and it uses a lot of power. TLB reach is the number of addresses in memory that can be accessed through the TLB. For standard paging, the formula for TLB reach is TLB reach equals the number of TLB entries multiply the page size. Greater TLB reach tends to increase the cache hit ratio, which improves effective memory access time, turnaround time, and throughput. To improve reach, one can make the TLB larger. However, increasing the page size will also improve TLB reach. However, this may lead to an increase in fragmentation for some applications that don't require such a large page size. Alternatively, most architectures provide support for more than one page size, and an operating system can be configured to take advantage of this support. Many modern systems are able to use multiple page size. For example, Linux systems support 4KB in huge pages. The ARM v8 architecture supports pages in the regions of various sizes. There are special bit fields in the TLB entries of this system that indicate the use of a larger page or region. Let's see in an example a process with 2 GB, and we know the page size is 512 bytes, and the size of the page table entry is 4 bytes. So first of all, the number of pages in the process is 2 GB divided by 512 bytes, which is 2 to 22. So there are 2 to 22 pages needed, and each page is 4 bytes. So 2 to 22 multiply 4 bytes, which equals to 2 to 24 bytes. Through this example, it can be concluded that for multiple processes running simultaneously in an operating system, a considerable part of memory is occupied by page tables only. So one solution is use inverted page table we introduced in Chapter 9. It consists of one page table entry for every frame of the main memory. So the number of page table entries in the inverted page table reduces to the number of frames in physical memory, and a single page table is used to represent the paging information of all the process. Through the inverted page table, the overhead of storing an individual page table for every process gets eliminated, and only a fixed portion of memory is required to store the page information of all the process together. So this technique is called inverted paging, as the indexing is done with respect to the frame number instead of the logical page number. Each entry in the page table contains the following field: the page number, the process ID, the control bits, and a chain pointer. The operation of an inverted page table is shown in this figure. The textbook cites an example where an array is laid out in row measure form, each row on a separate page. A program that initializes each array entry may incur many more page faults if it accesses the array a column at a time instead of a row at a time. This illustrates that the details of program layout and the address referencing patterns can affect process performance in a system with virtual memory. Compilers and loaders can help optimize performance by making judicious choices about where parts of the program are positioned in the memory. Hardware may provide a lock bit for each frame. When the lock bit is set, it means that the frame shouldn't be replaced. It is useful to lock kernel pages, user process pages with pending I/O, and the pages newly loaded but as yet unused. If I/O is pending on a page, and the page is replaced before the I/O happens, the I/O will take place between the device and the bad address. Commonly, all or a part of the operating system kernel is locked into memory. As an example of why this may be necessary, consider what might happen if a page X of the kernel memory management module was not resident in memory. What would happen if a kernel thread faulted on page X, and if X contained the code for handling the page fault? The operating system may lock a newly replaced frame F to make sure that the process P that owns F is allowed to use F at least once. If F is not locked, the operating system might select F as a victim for page replacement again before P has the chance to use F. In this section, we will describe how Linux, Windows, and the Solaris manage virtual memory. In Linux, it uses demand paging and a global page replacement. The page replacement algorithm is similar to the least recent use approximation clock algorithm. Recall LRU is a combination of using a queue similar to first in, first out, alongside using an array to keep track of the bits used to give the queued page a second chance, so it is a second chance algorithm. Linux maintains separate lists for relatively active and relatively inactive pages. Linux has a reaper process called ch10 that is triggered when free memory is below a threshold. ch10 selects pages from the inactive list and transfers them to the free list. There's more detail about Linux in Chapter 20. For Windows, on 32-bit processors, Windows 10 supports virtual address space up to 3 GB. On 64 system, it supports 128 TB virtual address space. Windows 10 supports multiple features such as shared libraries, demand paging, copy on write, paging, and memory compression. Windows 10 uses demand paging with clustering. Whole page clusters are fetched together following a page fault. A process is assigned a working set minimum and maximum number of frames, but these are not hard limits. Windows 10 implements LRU approximation clock algorithm for page replacement. The replacement policy is a combination of global and local. If a process faults when below its maximum working set, or when free memory is plentiful, the operating system gives the process a frame from the free list. On the other hand, if memory is below a threshold, and if a process faults when it has the maximum number of frames in its working set, then the operating system performs a local page replacement. Also, when free memory is below threshold, the operating system will take frames away from processes that have more than their working set minimum and put them on the free list. If necessary to replenish memory availability, Windows 10 will take frames away from processes that are at or below their working set minimum. Solaris performs global replacement. When a thread faults, Solaris always gives it a new frame. Therefore, Solaris gives very high priority to assuring that the free frames are always available. If free memory falls below the threshold, lots free, about 1/64 of physical memory, then the page out process, which is page daemon, starts running a two-handed clock algorithm. The front hand forgives. It clears the reference bit. The back hand reaps. It frees the frames that haven't been referenced, and the write them if dirty. After the page out process, frees a frame from a victim. If the victim falls on the missing page before the frame is reassigned, the operating system will reclaim the frame from the free list and give it back to the victim. The scan rate, which is the number of pages scanned per second, and the hand spread, which is the number of pages between hands, can vary. If free memory drops below a certain level, the operating system initiates swapping. The page scanning algorithm skips over pages belonging to libraries, being shared by several processes. The page out algorithm uses several parameters to control the rate at which pages are scanned, known as the scan rate. The scan rate is expressed in pages per second and ranges from slow scan to fast scan. When free memory falls below lots free, scanning occurs at slow scan pages per second and progresses to fast scan, depending on the amount of free memory available. The distance in pages between the hands of the clock is determined by a system parameter called hand spread. The amount of time between the front hands clearing a bit and the back hands investigating its value depends on the scan rate and the hand spread.